Good morning, good afternoon, good evening, and welcome to AI for Good. My name is Bastiaan Kost of the ITU, the International Telecommunication Union, and it's my privilege to introduce today's webinar, Improving Climate Models Using Machine Learning, as part of the AI and Climate Science series hosted by Professor Philip Stier. ITU is the United Nations Specialized Agency for Information and Communication Technologies, and is also the organizer of AI for Good. For this webinar, we will be using the Q&A functionality, which you can find at the bottom of your screen. Additionally, there is the chat functionality, which you can use to communicate with all other participants. Please make sure that your message is sent to all participants and not just to panelists. With that, I would like to hand it over to our moderator. Philip, how are you?
Great, thanks everyone, and apologies for the slight delay. Technical issues even creep in when you prepare well. But today we're back with not one, but two amazing speakers. So the program will be slightly different. So we'll kick off with the two talks and then really take questions and discussions of both of the talks in the end. But as Bastiaan already said, please free to add your questions in the Q&A anytime during the talk. But without further ado, to introduce today's speakers. So the first speaker will be Chris Bretherton, who is an atmospheric scientist and a leading expert on clouds and turbulence. And more recently, his group really has pioneered machine learning strategies to parameterize cloud processes in climate models, but also in the application of cloud resolving models, so higher resolution models to represent clouds better in climate models. Now he leads a new climate modeling initiative in what's now called the Allen Institute for AI in Seattle, and working with leading climate modeling centers to improve climate models. He's won numerous awards and prizes. I won't embarrass him here now. He's a fellow of the AMS and AGU, as well as a member of the National Academy of Science in the US. And with Chris today is Noah Brenowitz, who's a senior machine learning scientist for climate modeling at the Allen Institute, who received his bachelor's in statistics from NYU, and then went on to do a PhD in atmosphere, ocean, and mathematics science at NYU Current. And Noah's interests also lie at the interface of applied mathematics, machine learning, and atmospheric science, so they're just right here. And together, they will be speaking about improving climate models using machine learning, and we're very much looking forward to your talks. We didn't have time to rehearse the technical setup, but I'm sure it will work smoothly. Chris, over to you. This is looking very good. But Chris, we cannot hear you yet. I think you're still on mute. There we go.
Okay, fine. Well, thanks very much, Philip, for the invitation. And I'd like to kick off with a discussion of the first part of our machine learning effort at AI2, which is about improving climate models using corrective machine learning. I'll describe to you what that means shortly. And hang on, let me see if I can do this. So AI2's climate modeling group, of which I'm director, was started 2 years ago at Vulcan to pioneer software to revolutionize weather and climate models. We have two groups, only one of which we're going to talk about today. They were started in mid-2019 in partnership with GFDL and NOAA Climate Modeling Lab. And we are basically honing our techniques using versions of the US Global Weather Forecast and Seasonal Climate Prediction Model, FE3GFS. So the two efforts, the first one involves trying to make this model run faster on accelerator-based high-performance computing architectures to enable it to run at cloud resolving resolution globally for multiple years using something called a domain-specific language. The lead for that is AIfor. The part I'm going to describe today is
Chris, can I come in for 1 second?
Yeah.
The very right-hand side of your screen isn't visible. So at the moment, we're cutting off right next to Ollie. If there's no one to the right, then we're fine.
Okay, there. Is that better?
Much better. Thank you.
Okay, great. Okay, thanks. So the part we're going to talk about today, which is the group I'm leading, is to train machine learning on both very fine grid simulations and other reference data sets. And the way we sold our project was to enable more accurate rainfall predictions by coarse-grid global climate models that can run for centuries, that don't have the extreme computational requirements of global cloud resolving models. And we just moved to the Allen Institute for Artificial Intelligence on September 1st. The group is shown below. Noah, who's going to be speaking second, is part of the group. All of the members of the group contributed to the work we're going to be showing today. We have one member who's embedded at GFDL, Spencer Clark. And in addition, we have sort of a formal connection with GFDL too, and we work with Lucas Harris's group there. In particular, GFDL is doing the global cloud resolving model simulations, which I'll show you some results of today. So as motivation for this, we can think about the hydrologic cycle. And basically, the world, both the natural world and human world, are both adapted to the right amount of water, which in practice typically means the amount of water that they have got before, both the means and extremes, over the last few decades or centuries. And so this can involve issues like snowpack, drought, wildfire, extreme precipitation. And of course, climate change, as we know and we're experiencing now every year, is changing everything about that. And how are we then going to plan for this changing future? So climate models then are our window into the warming world. But climate models are not perfect. They do a good job, I think, enough job to guide us for the next couple of decades about what we need to do. But they find local precipitation trends harder to predict than temperature trends. So for example, these two plots show decadal means for the US Pacific Northwest, a 3-state average. So the black line here is the observed temperature record from 1900 to the year 2000. And the gray lines are projections of models, CMIP models doing historical simulations and then a scenario simulation of increasing greenhouse gases up to 2100. And you can see that all the models do differ from each other significantly, but they all predict a large temperature increase. I apologize for the units. On the other hand, if you look at precipitation, if you look over the last century, the decadal trend is basically zero. There's a lot more variability. That's what all of these climate models predict. But going forward in our particular region, there's a certain group of 5 models which predict increasing precipitation, and another group which is predicting decreasing precipitation. And it would be really nice for planning of hydropower, agriculture, et cetera, to know which of these is more likely to be correct. So the question here is whether big data, machine learning, and modern computers can help with this. Well, okay, probably most of you are familiar with climate modeling, but just to get the idea of the philosophy of our machine learning, let's just review some very basic elements. So a global climate model simulates weather and its interaction with land, ocean, and ice surfaces for a very long time, decades to centuries to millennia. And the way that it does this is that it simulates equations for temperature, moisture, winds, and other things on a 3-dimensional grid. What's important for this talk is that those equations consist of rates of change, which involve the airflow that's resolved and simulated on the grid, plus other processes. And it's these other processes which we're going to try and machine learn. Typically, we use human designed parameterizations to represent these other processes, which include things like clouds and rain, small scale air motion, radiation, surface interactions, since Philip is here, aerosols. And these processes are quite complex. In many cases, we don't fully understand how to represent them, especially on a coarse grid, but they mostly work column-wise, especially when we consider the 25 to 100 kilometer wide columns that we use in a climate model. So again, using our machine learning, we're going to try and replace human designed parameterizations by machine learned representations, but we're also going to make the assumption that that machine learned representation works with the grid resolved airflow already predicted by the model. So we're not going to replace that part of the model, and that it works column-wise. And we're going to then train the machine learning based on some form of a reference data set. And we'll describe two forms of reference data sets in a second. Well, part of how I got interested in this was working on physical parameterization of clouds and turbulence, and realizing how difficult it was to improve on the already reasonable ideas that had come before, given the great complexity of the small scale variability in a lot of physical processes that we're trying to represent in a very simple way. But another thing that was inspiring is how realistic very high resolution global atmospheric models can be. So on the left here, we can see a picture of a 50-kilometer global climate model, not a particularly modern one. What's shown here is cloud in white and precipitation of various intensities in green and yellow. And if we look at this, you can see that the representation is clearly pixelated and spotty in places, intermittent in ways that are not fully realistic. So the picture in the middle is a global simulation by the FE3GFS model run at NOAA, or run at GFDL, run at 3-kilometer horizontal grid resolution with 80 vertical layers. And you can see that it looks almost indistinguishable from the satellite picture on the right. Now we're here about 2 days into a simulation. So at this point, the simulation is still feeling its initialization. So that's why the individual weather features look somewhat similar, but they also have similar structure, similar cloud patterns, and so on. So it does seem like there could potentially be a lot to be gained from using very fine resolution global models. And this isn't just true through the eyeball norm. If we look at actual rainfall time means, we find that this is also true. So here from 40-day simulations, and these are meteorologically nudged simulations, I'll say. I'm not going to describe what that means, but it means that even with 40 days, it's reasonable to compare the rainfall patterns of these simulations with observations. And here, blue indicates negative biases and red indicates positive biases with respect to state-of-the-art observational data set for the same period of time. And what you can see is that the 200-kilometer version of our model, which is the version that we're going to try and improve, has significant biases over the Himalayas, high biases in, say, the Sahara and Sahel region in particular, over Africa, where there are blue or negative biases. And the 3-kilometer model is actually considerably reducing these biases and others as well. And this isn't an accident. This is enabled by the 3-kilometer model explicitly simulating both cumulonimbus cloud systems, which are important for tropical rainfall and warm season rainfall almost everywhere, and also resolving mountain features much better. So in general, then, the way our machine learning is going to work is it's going to try and make our coarse-grid model, the 200-kilometer model you were seeing, evolve more like a reference. And the reference can be one of two types. We'll show examples of both. The first kind of reference is to use a global observational analysis or reanalysis. So this involves diverse observations synthesized and gridded by a weather forecast model. So examples are, for instance, ERA5 is a very commonly used reanalysis. These analyses are available over 40 plus years, but the big gotcha here is, of course, they're only applicable to the observed, i.e. present day climate. The other kind of reference we're going to use is a fine grid model. So a fine grid model is a high fidelity simulation, like the 3-kilometer simulation we saw. So it might be more accurate than a coarse resolution model, but we don't know that it's the truth. The big advantage of this, though, is we can run such a model in new climates, not just the one that we have. And so we can then potentially use this to extrapolate our machine learning to new climates. And either way, the corrective machine learning method that I'll describe involves nudging the coarse resolution model time step by time step toward the reference state. And then machine learning the nudging tendencies needed to do this. So the nudging tendencies then are calculated based on the difference in state between the coarse resolution model, state represented by A below, and the reference model, in this case, observations, represented by A obs. And so the nudging tendency is just the difference between A minus A obs over some kind of a nudging timescale, which we pick as 3 to 6 hours for empirical reasons, but also ones that have a good justification. And the reason that we use this approach is that it avoids issues that we would otherwise have of initialization shock to the coarse resolution model if you would start it with output from a fine resolution model. Now, I want to note a couple of other problems. Noah will also mention them. They're an issue for any kind of machine learning where we're going to couple the machine learning to other components of a model. So in this case, we're coupling our machine learning to both fluid dynamics, and because it's a correction to the parameterized physics, we're actually coupling it to the parameterized physics of the coarse model too. And so the machine learning is interacting with these other components. There can be feedbacks between them, which are operative when you run the model online. But when we train the model, the other components, we actually know what they're doing, and we're just trying to optimize the machine learning itself. So offline training doesn't guarantee a good result online. And in particular, things that can go wrong are that your simulations can be unstable. They can just blow up. They could give inaccurate weather forecasts. And that's important because since weather is averaged to create climate in these models, inaccurate weather means your climate is on a flimsy theoretical basis. Or even if they give accurate weather forecasts, you could have climate bias. So making sure that none of these things happen is the essence of online machine learning skill. Okay, so how do we do this? Well, we have used both random forests and neural nets for our machine learning. But either way, the technique is basically the same, at least for learning the nudging tendencies. So our inputs then are profiles in the 79 vertical levels of the model of air temperature, specific humidity, and optionally the horizontal wind components, along with some auxiliary variables, such as land sea mass, the solar zenith angle, the height of the terrain, etc. And then the outputs then of the machine learning are going to be estimates of the nudging tendency profiles for temperature, moisture, and winds. And we basically select times out of our training data set, our nudged coarse resolution training data set, to calculate or to get the nudging tendencies and the inputs and do the machine learning. And we're using multiple millions of samples of columns for that purpose. Now, we also use neural nets. When we use neural nets, we do things a little bit differently, but they're shallow nets. They have 2 hidden layers and 128 neurons per layer. And another thing that we found useful in some of our work is to also correct the surface radiative fluxes that are predicted by the model from what the physical parameterizations produce because of cloud biases in the coarse resolution model. This helps couple the land surface model more accurately to the atmosphere. Okay, well, the way we do this is actually sort of interesting. At the Allen Institute, we don't have our own HPC, and because of NOAA's security requirements, we also don't, from AI2, have access to their high-performance computing. So our person at GFDL plus other GFDL staff do all the fine grid simulations on their supercomputer Gaia, which sits behind a firewall. Then they put that on Google Cloud, coarse graining the results on the fly, so we don't have to save the whole simulation. And then our entire machine learning workflow relies on cloud computing. In addition, another novel feature of what we do is to facilitate our machine learning. We wrap the Fortran-based climate model main loop in Python, and then we can add Python components to the model when we run it at coarse resolution on the cloud. Okay, so first I'd like to show you something we call nudged observations, or nudged obs machine learning. So here we're trying to train our machine learning using an observational reference. And this is work that's recently been published in GRL. So here then, what we do is we take an analysis. In this case, it's actually an analysis made with the GFS, which is the same model that we're actually trying to machine learn improvements to. It's not quite the same version of the model, but at least by minimizing that incompatibility, you sort of are avoiding unnecessary issues with machine learning. And then basically we're trying to learn the correction. And what we find is if we run this model at 200 kilometers, which is not commonly done, the model does not actually like to precipitate when faced with the observed atmospheric state. It precipitates too little. And as a result, then the nudging is forced to do more precipitation, remove more water from the atmosphere. So we see almost everywhere in time mean, we see column drying in the nudging tendencies. So the nudging tendencies are trying to dry the atmosphere by an average of 1.2 millimeters per day globally, which we can interpret as the machine learning needing to do additional precipitation that the model isn't doing. So the machine learning then, the data set is on the left, averaged over our testing period. And on the right are the predictions from the machine learning averaged over that testing period. And you can see we capture those patterns quite well. Now, in addition then, in time mean, we also capture the vertical profile of the column drying quite well. And obviously we do this for the other fields, the heating and the momentum tendencies as well. It's interesting to look at them, but we're not going to in this talk. However, if you look at instantaneous transects, I don't know why we're in slideshow mode here, then things are very noisy. Actually, the field we're trying to predict, the left field in the lower right panel, you can see it's a mess. That nudging tendency has all kinds of noise in it. And so as a result, when we try and predict this, we predict only a smooth version of this. We can only actually learn about 20% of the variance in the nudging tendency because it's so noisy. So it's not actually that easy a machine learning problem. However, using the machine learning, we are actually able to significantly improve the performance of the model in making both forecasts and also its climate. So for instance, if we look at forecasts using the 200-kilometer FE3 GFS, black indicates the model with no machine learning. And here we're looking at the root mean squared error, globally averaged, of surface pressure as a function of forecast lead time. So it starts at 0, and it gets large as you go to large forecast times. But if you then add the machine learning correction, you get the red. And the shading here indicates the fact that we're actually doing multiple forecasts. We're doing one forecast a month for 12 months of the year, and this is an average over all of them. And the shading is the monthly variability of those forecasts. But what we see is, on average, then we gain about an additional day of forecasting time lead. So 4.5-day forecast with the no machine learning model as skillful as a 5.5-day forecast with machine learning. So this is actually quite a significant improvement in forecast skill. And same thing for lowest layer temperature of the model. We again gain almost a day of forecast skill. So that's nice. But also of significance, since we're sort of trying to use this in the end for climate modeling, is that if we look at annual mean precipitation relative to the observational reference, GPCP, which is actually not derived from the same analysis that we actually nudge to, what we see is that we actually reduce the pattern errors, that's the RMSE here, in precipitation by about 20%. So in particular, so red and dark blue would indicate large positive and negative biases relative to observations in annual mean precipitation. Baseline model has a lot of problems over mountain ranges, predicting too high precipitation. And the machine learning greatly reduces those biases. Same over Central Africa, the biases are also reduced. And this is encouraging because the machine learning is not explicitly trained to optimize precipitation. There's no part of the loss function that includes precipitation. So now then I'd like to turn to our other form of machine learning, which is what we call nudge to fine. And this is like nudge to observations, but now the reference is coarsened output from the fine grid simulation. So here, this is an example from a different model, but here we imagine we have 3-kilometer output of something. In this case, what's being shown is clouds, but it could be humidity, temperature, et cetera. From your coarse resolution model, you coarsen it by averaging along horizontal surfaces. Even if we have terrain, we use horizontal surfaces for the averaging to the desired coarse resolution of 200 kilometers. And then we save those coarse resolution fields for as the reference for our machine learning. So it turns out that we learned something from our nudge to observations work, which is that our coarse resolution model actually has substantial radiation biases. So in particular, if you look at the surface downwelling radiation in the fine model, which is our reference here, versus the coarse model, we find that the coarse model has too much downwelling radiation. Too much sunlight reaches the surface because there's too much cloud. Too little cloud, excuse me. And so we actually have to correct that bias, or the result is that the land surface cooks and it starts to release too many latent heat fluxes. And also we get too much precipitation, which moistens the land surface further. So what happens then if we don't correct this then is we end up with the panels in the center, which are time mean sensible latent heat fluxes over our training data set time, which is 40 days. And we see large biases. So the red indicates a very high latent heat flux bias over land. So basically, as a result of too much sunlight on the land, coupled with too much rainfall over the land, we get far too much evaporation, which then contaminates our training data set. So to avoid this, we actually prescribe the radiation and precipitation from the fine resolution model for the training data to keep the land surface from drifting. And furthermore, in the coarse resolution machine learning corrected model, we actually machine learning a correction to the radiation to make it match the fine grid radiation. And this then considerably improves our precipitation over land. So with this then, we are able to improve the mean precipitation error over the period that we can compare or run with the fine resolution reference, which is 40 days, by about 30%. And again, the way things improve is that things get a lot better for mountains and over Central Africa, and modestly better in other places. Again, we use a shallow neural net here. A random forest works nearly as well. And we make machine learning corrections here to temperature, moisture, and not winds, because with winds, it doesn't really show up in this field, but winds, if you make machine learning corrections to them, in the end, the upper atmospheric temperatures drift, and we didn't want that to happen. And in particular, a particularly impressive part of this is if you look at the distribution of precipitation globally averaged between land and ocean. So in global mean, whether you look at the baseline model or the machine learning corrected model, so the baseline model is in gray in the lower right panel, and the machine learning corrected models, random forest and neural net, are in blue and brown. What you see is that the baseline model has good global mean precipitation, but its land precipitation is way too high and its ocean precipitation is too low. And with the machine learning, we're able to almost totally correct away that error. And again, this is without explicitly training to do better precipitation. Another thing that we do a better job on, at least in terms of amplitude, is the diurnal cycle over land. So here, the baseline model has a diurnal cycle. It actually doesn't have too bad a phase, but its amplitude is too small by about a factor of 2. It's pretty irregular, and the land mean precipitation is too high. And with the machine learning, we get the right amplitude diurnal cycle, but it's still phased 3 hours too early compared to the fine resolution reference. Now, I do want to point out that the machine learning corrected simulations aren't free of drifts. If we correct just temperature, moisture, and surface radiation, and we look at some things, and so here, fine grid model, that's the reference, is the black dash, and brown is kind of the model to take the most pay the most attention to. That's our neural net machine learning model. And the solid sort of gray-black is the baseline model. So if the brown model is closer to the black dashes than the gray model, then we're doing a good job. We're removing drifts. And we see that that's true for some fields, like in this case, 200 hectopascal temperature and precipitable water, but it's less true for the zonal mean of 200 hectopascal temperature, where we can have some pretty big errors in mid-latitudes, or 850 hectopascal temperatures. In both those cases, we do roughly similar to the baseline. Okay, so in conclusion then, corrective machine learning enables a coarse resolution global atmosphere model, in our case, the 200-kilometer FE3 GFS, to make both better weather forecasts and better time mean rainfall patterns compared to a reference, which could be observations or a fine grid model. We are also applying this right now to fine grid simulations made over a range of climates, using specified sea surface temperatures ranging from 8K colder than present to 8K above present. And this is mostly working, but we're still working a couple of bugs out of this. And I guess lastly, I want to point out that this actually complements traditional climate model development. Can be adapted in the form I said to any global atmosphere model. The nudging tendencies from the training model run actually tell you a lot about systematic biases of the baseline model parameterizations at coarse resolution. And the machine learning correction does a good job of reducing some biases that human design schemes have a tough time with, in particular over orography and the land rainfall diurnal cycle. But it has problems. Machine learning schemes don't automatically build in all the conservation constraints and physical constraints that human design parameterizations have, and that can make them drift or blow up even in unseen climates or weather conditions. So that's it. Thanks.
Great. Thank you very much, Chris. A fascinating talk and really interesting results. So I think we will take most of the questions after both of the talks. So if you have questions, put them in the Q&A now, and we will pick them up with the discussions. And now we go straight to the talk by Noah. And hopefully that screen sharing works. It seems to at least kick off. We didn't have, and it looks perfectly, Noah, after all these worries. I think you're ready to go.
Hi, can you hear me?
Yes, loud and clear.
Okay, great. So yeah, just let me know if there's any issues and we can adjust. So yeah, I'd like to thank the organizers for inviting me to speak and kind of giving me free rein to choose the topic. So I'll be presenting on some ongoing work that we've been doing using machine learning to emulate existing physical models, specifically the parameterization suites individually and as well as the whole suite of a particular weather model, the FE3GFS weather model. So it's important to note that this work has been done closely with another AI2 scientist, Andre Perkins, as well as a summer RA from the University of Washington, Jacqueline Nugent. So given that our group has demonstrated some success learning from high resolution simulations to improve coarse resolution models, which Chris just talked about, why do we go back, kind of take a step back and do emulation? Well, the simplest answer is imitation or emulation is sort of our way of paying homage to existing parameterizations, which have gotten us quite a long way. Moreover, they also provide an interesting test problem with many of the features and complexities that are required from learning from high resolution climate models. So our interest in this is less about accelerating climate models using machine learning emulators, but more about drawing insights from this machine learning problem and extending that to other settings. Oh, sorry, yes. So here's the slide of a good Oscar Wilde quote. So what are physical parameterizations? They are portions of a climate model that, when acting in concert with the dry fluid dynamics, produce a weather or climate simulation. So examples of physical parameterizations include the radiant transfer code, both long wave and short wave, one of the most expensive portions of a climate model and a key target for emulators. Another portion is the cloud microphysics, cumulus convection, boundary layer turbulence, gravity wave drag, etc. So one common assumption that these parameterizations make is one of column locality. So typically a parameterization is assumed to depend on inputs only from a single atmospheric column, namely a vector of inputs extending from the surface to the top of the atmosphere above a single horizontal location. Now this assumption is well founded because the atmosphere has a large aspect ratio, and so in many ways it mixes more quickly in the vertical than it does in the horizontal. So typical inputs to a parameterization include typical atmospheric state, such as humidity, temperature, the sunlight, surface elevation, other aspects of the land surface or ocean surface. And the outputs are quite simple. They are tendencies of heating, of temperature and humidity, wind, and as well as the winds. And so these are usually cast as rates. So one thing that's cool is that I've posed this parameterization as one of taking inputs to outputs, and this is something that machine learning can do quite well. And so if we then view these inputs as sort of machine learning features, we can concatenate them into one vector, and we can either use a Fortran code shown here to predict these tendencies as the outputs, or we can use machine learning models like a random forest, tree-based model shown in the middle, as well as a neural network. Any of these will tend to produce the same outputs. So as an input-output problem, it's a very clear supervised learning task. And that's why it's such a great test bed. As opposed to learning from high resolution data, this is a perfectly supervised task. We know that if we can perfectly predict the same outputs as these physical schemes predict, then we'll be able to drive a climate model successfully with them. So as a result of its simplicity, the emulation has probably been the first application of machine learning to climate modeling that I'm aware of. And thus far, emulation efforts have typically focused on individual schemes. So going back to 1998 and the early 2000s, there's been people using different types of machine learning models, including neural networks, as well as tree-based models, to replace the radiative transfer component of the model, which I said is one of the most expensive portions of the model, and thus one of the most potentially attractive to replace with computationally efficient emulators. Then in the mid-2010s, it seems that there is a bit of a hiatus in the development of these kind of schemes. And since then, there's been a resurgence with more recent focus on the radiative transfer, as well as on other physical parameterizations, such as the deep convection. This was done in an idealized setting, gravity wave drag, and I'm sure I'm missing some important citations here. But the work that's inspired us mostly recently is this paper by Alexei Volochevsky and Vladimir Krasnopolsky out of NOAA, where they replace the entire suite of model physics with a single neural network. And this is the problem that's most analogous to what we're trying to do with high resolution machine learning, rather where we don't have available this sort of decomposition into different physical processes. They're all kind of merged together in our high resolution data. So we figured that solving this problem of full physics emulation could give us insights about solving other problems as well. And so the sort of takeaway result from this is by replacing the whole physics suite of the same model that we are actually using, they're able to get a classic, one panel looks just like another panel plot. So in the upper left, I'm showing that a zonal average versus vertical level climate average of specific humidity from a neural network as well as from their control. So you can see, well, they look identical. This is perfect. And the same result for cloud water. So these are really impressive results that show that effectively their emulator is indistinguishable from a much more expensive suite of Fortran code. And so I'll have to be honest, we've somewhat struggled to reproduce these results. And I'll give you a little bit of a blow-by-blow why. So the initial attempt was we took the same atmospheric model, FE3GFS, with a slightly different configuration, different microphysics, and a different turbulence scheme. And we tried to use a very similar neural network setup. And we weren't able to actually obtain very stable results online. So we had poor offline performance. We weren't able to get skillful ML prediction, even of the training data for most of the water species like cloud water. These are quite challenging fields to learn. And then online it blows up. And since then, we've been engaging in this sort of bisect algorithm to try to get closer and closer to their configuration. So we've changed the microphysics to Jiao-Car. It's a simpler scheme and it's the one they use. Still weren't able to achieve success. We've changed the boundary layer scheme to hybrid EDMF, which is the same as they were using. And so we've made some improvements there, but we still haven't quite achieved that high bar that they've set. And I think the reason is that it's hard to nail down all the differences between our configurations. And this speaks to the reproducibility of this kind of machine learning research, is that, so for instance, they've used data that's been regridded to latitude and longitude grid, whereas we've been using data that's on the native model grid. They have a slightly different subsampling in space and time. And then there's many different differences in the machine learning hyperparameters, optimizers, as well as the machine learning packages they are using. So it's really a lot of work to get to exactly emulate their setup and reproduce their results. And so I think thinking about how to bridge these gaps is important going forward. And so I was speaking a bit about not achieving success, and I just wanted to talk about that more. And Chris did already show this slide. But by success, we sort of have a hierarchy of needs. The first is an offline skill at the basic machine learning task as it's been posed. And we hope that we think this is a prerequisite to having online skill. And really in this work, we're currently mostly focusing just on this sort of bottom, just the survival part of the Maslow's hierarchy of needs. And we need to have stable simulations, and we haven't quite achieved that reliably yet. So our current best configuration for this full physics emulator is similar to Vladimir and Alexei's configuration, except that we use relative humidity as our prognostic variable for doing the stepping rather than specific humidity. And we find that this actually leads to more stable simulation because it sort of bakes in some physical constraints, as well as deals with the fact that humidity can sometimes, ranges over so many orders of magnitude. Relative humidity is a sort of a more regularized machine learning input. And as well as some auxiliary features such as latent heat flux and other aspects of the land surface and of the atmosphere that we think are important for machine learning, but which are not actually variables that are being propagated forward in time or predicted. So one aspect of this is we're not using predicting tendencies for all the variables. We're only using tendencies to predict winds and temperature. But because cloud water is such a fast variable and it responds so quickly to the other aspects of the atmosphere, we directly predict the state after the action of the physics scheme instead of predicting a tendency of that state. And we find that if we predict tendencies, we'll tend to produce a lot of negative cloud water. But by predicting the next state directly, we are able to reduce this amount of negative water. And for those interested, we use fairly off-the-shelf set of hyperparameters that we did do some hyperparameter tuning to achieve, especially tuning the learning rate of the optimizer as well as the momentum of the optimizer. So with this setup, we achieved pretty good offline skill. Here I'm showing offline skill for 4 different fields: humidity, meridional wind, zonal wind in the lower left, and temperature. The x-axis is time in a simulation. And then starting from, you can see the date here, starting in August of 2016. And then the y-axis is vertical. So we can see, for instance, looking at the humidity, that we have quite good skill. This measure of skill measures the improvement of the emulator over predicting 0. So if you do worse than 0, it's probably better to do nothing at all. And so 1 means that we've achieved almost perfect skill at this problem. And we do that pretty well in the upper troposphere and less well in the boundary layer, and horribly where there's almost no humidity in the very top of the atmosphere. And it's a similar story for the other fields. Notably, we do quite well in the boundary layers for the other variables, and the temperature, we do quite a good job with temperature. So really, humidity is a more challenging field to predict with these emulators. So that was offline skill. In terms of online skill, we assess this through so-called piggybacking. And so this is actually a very old technique. It's been done since ancient times, as you can see here on the right. And our basic idea, which is more recently inspired by work by Wojciech Grabowski at NCAR, is to piggyback the baseline physical suite while applying active updates from the ML emulator. So the basic piggyback model time step looks like: first, compute the full parameterization suite, then ignore it, but save its outputs and apply the ML emulator instead. And then after the fact, we can compare these emulated physical tendencies with the actual physical tendencies that were predicted. When we do this, we get similar plots to what I showed before. So we can see that overall, the online skill that the emulator has at predicting the piggybacked physics is almost as good as the offline skill, but does show a little bit less skill than it did for humidity. And then for temperature, we similarly see that the temperature actually is quite skillful over the first. This is over a relatively short time period of 3 hours. I will note, just as a bit of foreshadowing, that the spun up initial condition, that this simulation was initialized with the spun up initial condition 10 days after the training data was initialized. If we initialize on the second day of the run, we actually get much different results because the baseline physics have not equilibrated yet. Unfortunately, if we run these simulations longer, 3 times longer, eventually they crash. But this crash is somewhat of a sudden nature, and we think we'll be able to debug this. So like I said, this is ongoing work. Now, one really interesting aspect of this, which I hadn't really realized was cool, was that if we initialize with a non-spun up state, the emulator actually has significantly more regular behavior than the baseline physics do. So the yellow curve here is the baseline physical suite when initialized. This is 1 day after it was initialized with a reanalysis product. And we can see that the blue line is the emulator. And the field being plotted is the sort of net heating or a measure of precipitation or vertical velocity. You could plot any of those. And you'll see that the physics is really up and down over this initial time period, whereas the emulator has a much smoother initialization. So we think that this could actually have the property that emulators can be initialized more easily than existing physical packages. And this could have all kinds of applications in data assimilation as well as weather forecasting. Now, moving on from the full physics, we've seen we haven't quite achieved success with the full physics emulators. So we return to this task of emulating individual parameterization in the hopes that maybe we can get better offline skill and then better online skill as well. So for this problem, which Andre Perkins and Jacqueline have been working on a lot, we considered 3 different models. One was a linear model baseline. It's always good to start with a linear regression when doing machine learning. And then we had a couple of more complex machine learning models. The first was a very similar sort of dense neural network to what I showed for the full physics emulation. And the second was a recurrent neural network recursing over the vertical axis pointing down. And so this is one way of enforcing the fact that most microphysical schemes will have a downward dependence of their outputs with respect to their inputs. So the tendency at a given level for a given field will only depend on things above it. And this is because rain tends to fall downwards rather than upwards. And so when we look at this same sort of skill improvement ratio metric, we can see that an x-axis here is the vertical axis and y-axis is the metric. We can see that the RNN, which enforces this sort of physical constraint of downward dependency, achieves really good skill. So almost 90 to 95% accuracy, except where the humidity is very small, above level 50. And so we're quite happy with these results. This is probably by far the best offline skill we've seen on any machine learning problem in our project thus far. Online, it does reasonably. So if you look at global average cloud water mixing ratio, time and the x-axis and height again on the vertical axis or model level on the vertical axis, you can see that the cloud water fields seem to have we're not removing too much cloud water. Overall, they tend to agree, although there are some differences at short times. until a very sudden crash around 7 days into the forecast. And so, and then this crash might be related to mean state drift. So here I'm showing the global average of water vapor. This crash might be related to sort of developing drifts in the simulation. So we have this interesting result that we've achieved remarkable offline skill at this particular emulation task, but yet we still have not achieved the kind of online stability that we'd like. And so this is sort of really pointing to the fact that online is not the same thing as offline skill. So yeah, emulation is a tricky machine learning problem. One reason is that climate model physics have many different time scales. Microphysics and phase changes occur on seconds. Boundary layer turbulence is also quite a fast process from minutes to hours. Deep convection is slightly longer, hours. Irradiation can be days to weeks. And the dry dynamics, we have propagating signals in the deep tropics that have intraseasonal timescales. And so the combined action of all of these different processes is what defines the equilibrium climate. And this is the superposition of timescales is part of why we get really challenging machine learning problems. And just to demonstrate just how challenging this problem is from an offline sense, I showed a couple of results here. So here's some visualizations of tendencies that the baseline model is predicting 10 days after initialization. So this should be kind of as smooth as these tendencies will be getting. And so one is they're quite sparse. Usually, most places there's 0. Other places they're quite large. And then there's also sort of, you can see that there's different physical time scales involved here. So you have a deep convection type event here, and then boundary layer, sharp boundary layer features. So this is really a challenging sort of image to emulate. And on the right, I'm just showing how crazy non-Gaussian this data is. So this is a log PDF diagram, so Gaussian with the same mean and variance as the physical parameterizations tendency distribution is shown as a parabola. And you can see that the baseline physics have highly non-Gaussian PDF with really, really fat tails. So this is not a particularly easy offline machine learning task. Just wanted to note that a particular tool that we've been using to do these simulations, because I know this has been a challenge for a lot of different groups, is how do you actually do machine learning in a hybrid modeling context where the host model is usually written in Fortran. And we've been using a library called CallPyFort to do this. And so the idea is to embed a Python interpreter in Fortran. And the advantage of this approach compared to other approaches is that this allows you to basically to call a particular subroutine without refactoring the whole model to do so. So this allows you to go into a very small, very low level of the code and replace a specific subroutine and monitor its inputs and outputs. And we find that generally there's, for our research purposes, where 10 or even a factor of 2 loss in performance is not really significant for our kind of prototyping. We find that there's relatively minimal performance penalty, mostly because machine learning libraries are fast and the actual communication between Python and Fortran is not that slow. So if you have any questions about this, I'm really happy to help others set up this use this library in their own codes, and we've used it in a variety of contexts as well. So I think it could be helpful to the community. So in conclusion, we've struggled to reproduce this remarkable full physics emulation result from Krasnopolsky and Bolachevsky. This is probably due to just sort of a slew of small differences, both in the training data set, the way it's sampled, as well as differences in our machine learning code. And to me, this really points to the need for more collaboration across groups as well as perhaps more coordination between many groups on how to both, you can't just share your data, you have to share your model configurations, you have to share the codes, you have to share the environment in which these codes were executed. And so it's not as simple as just sharing a data set and hoping that it works. So I think this points to the need for collaboration. The emulation problem is a challenging machine learning problem, but nonetheless, we do achieve good skill offline, and we have promising results online. Thanks.
Great. Thank you very much, Noah and Chris, again, for the fascinating talks. This was really great. So we have quite a few questions already in the Q&A, and we'll, Noah, if you end your screen share, then we can get both of your faces up if Chris wants to come up as well. And I think we will just go through the Q&A now and encourage people to still add more questions as we do that. So I'll kick off with a question to Chris, which was here, and that's from Alison Douglas. What machine learning methods do you use for the nudging, actually? And for the neural networks, have you tested also other architectures than the one you described? Not sure, we don't have Chris back yet. I think there's some.
Okay, fine, yeah. So sorry for the lighting. So we've used both random forests and neural nets and demonstrated that to a large extent, they actually give pretty similar results. As I mentioned in the talk, we're using shallow neural nets because our machine learning is actually pretty noisy. And so I think deep networks work better when you sort of can more exactly emulate your data set. But in our case, we can't really do that so well. We have thought about or started trying to explore some other architectures like convolutional networks, and in particular thought about the possibility of relaxing the column machine learning assumption, potentially using some form of convolutional approach in the horizontal. But really, so far, our goal was to actually demonstrate that we could do anything and improve on the skill of a coarse resolution model. And so we kind of focused on that at the expense of trying to do perhaps the best job in using the best machine learning to do something.
Great. Yeah. No, there's a question, a good question that follows on right from this, from Peter Watson. So this one's also to Chris. Do you think that the failure of the neural network then to capture a large fraction of the tendency variability is more because it has failed to learn a large part of the signal, or because there's just so much large stochastic variability?
Yeah, that's a really good question, and I don't fully know the answer. I do think that there is a lot of the variability that isn't necessarily captured by our feature set. So recall that we're actually trying to basically learn the difference between what's going on in the fine resolution model and the coarse resolution model. And what's going on in the fine resolution model certainly isn't just a function of the column, the horizontal column domain averages over of the fine resolution output over a coarse resolution grid. There's like memory effects and things like that. And even in the coarse resolution model, the set of features we're using isn't the same as the set of the physical parameterizations we use. So we're not necessarily using things like the cloud water at the previous time step. So we are throwing away a fair amount of information, and I do think that's part of the reason the machine learning doesn't capture a larger fraction of the variance.
Great, thanks. And then there's a question, I think, to Noah from Angelo Penado Bravo, who asks, what do you think to use about the use of LSTM, which might capture the effect of variable time dependency a bit better? And what about more physical neural networks to emulate the physics in a better way? So embedding physics constraint, I guess, is a broader question.
Yeah, thanks for the question. Yeah, so the full physics, we convinced ourselves reading the papers for these, actually read the papers for the parameterizations, and found that these schemes actually do have a recurrent nature and time. So they kind of they save out their own tendencies and then use them the next time step. So so it does have recurrent nature and time. So we found that adding those inputs didn't actually improve the skill for the microphysics emulator by much. So we kind of put that aside for now. But I do think that sort of training recurrent architecture is a good idea. Although to do that, you'd have to save out the data for every single time step. And so it's a bit of complex from a training perspective. I forget the second part of the question. But.
It was basically about more explicitly embedding physical constraint, which could also address some of your drifts that you sort of seem to observe.
Yeah, I mean, for sure, like definitely it will help with, one physical constraint is that humidity should be positive, precipitation. So these kind of non-negativity constraints, we've been training models in the presence of this and in other contexts. And so I think that's kind of where our thoughts lie in terms of improving some of these sudden crashes, for sure. And it's very easy the relative humidity is sort of an example of that, where we actually do a transformation from specific humidity space to relative humidity space before doing the emulator, and then a transform back out. And so the model can be trained, for instance, to predict the error for the model can be in specific humidity terms, but you can still have internally it be enforcing this kind of relative humidity structure. And so that's one example of what you can do with neural nets. You can't do that with the random forest as easily. So.
Great, thanks. So I think there's a follow-up technical question also for you about the thought of combining CNN and RNNs. And I'm not sure if you thought about it, but the question is there.
Well, they're kind of in either or, right? I mean, so we're using RNNs in the vertical direction, not the time direction necessarily. So to enforce a certain kind of causal structure that exists in the microphysics scheme, where it just depends on points above. And so when you have that kind of causal structure in your model that you're trying to emulate, you could use the CNN as well. So there's something called causal convolutions that you could use to force that you have the kind of upper triangular structure in the dependency or the Jacobian of the model. But yeah, our CNNs will be faster is one advantage.
Great, thanks. Then there's a question by Sarah Bretherton, who asked Chris, and I think it's a very good question. So can we explain the source of biases in the physical dynamical model from the machine learning parameterization? So in short, can we learn something about the underlying physics in limitations of the dynamical model from the machine learning emulation?
Well, definitely I showed the example of the 200-kilometer FE3 GFS not raining enough when confronted with, say, the observed atmospheric state consistently. So in that case, the nudging tendencies basically show you that problem is worldwide over land and ocean, and so they kind of show you what you're aiming at to improve the physical parameterizations. So that's is one aspect in which we can use the machine learning tendencies to help. In that case, it's just the nudging tendencies, not even the machine learned nudging tendencies. A separate question, which you might have also been looking at or thinking about, is why does the model with the machine learning correction still produce climate drifts? And I think there really the answer is you can try and optimize your model to. We're optimizing our model basically to improve the single time step performance of the coarse resolution model to look more like the fine resolution model. But the machine learning still can't do a perfect job of that. And so as a result, there's every reason to think that there will be some drifts. I think one thing that's interesting that I didn't focus on here is, especially with neural nets, if we use different random seeds, we find that the drifts are actually quite sensitive to the seed, that it's the loss function that we have doesn't necessarily constrain the climate drift a lot. And I think that provides a lot of hope that we could actually put an additional layer on top of our machine learning, whereby we could actually adaptively control the drifts and produce a somewhat drift-free climate with the machine learning correction while still maintaining the weather forecast performance. But we haven't done that yet.
Great, thanks. And then there's a question from Christina Redin, who asks, how could machine learning, and that is a very broad question, could it obtain good results without this simulation? So just based on the input data, would that be enough to make good climate simulations?
Is that to me or to Noah? Or
feel free to choose.
I guess it must be to me because it was at 8:44. I guess I'm not quite sure how to answer that question, because the fine for our, when we are trying to use the fine resolution data as the reference, obviously we need the fine resolution simulation, and the way that we do the machine learning is right now is to run this nudge training run. Now, what we could have done, and what we in fact tried to do before this, is we tried to initialize our coarse resolution model directly with the coarse and fine resolution data, and just look at how different the initial tendency of the coarse resolution and the fine resolution models were. But the problem you have with that is something called initialization shock. The coarse resolution model doesn't like the fine resolution initialization. It's not even mass balanced. And so you produce this very strong sea of vertical velocity spikes on the grid point level, especially around regions of topography. And so the nudging, which kind of sort of forces the coarse resolution model to the fine resolution more smoothly, ends up being essential for not provoking initialization shock.
Apologies, I was frozen a bit for myself, so the departmental internet also gave in for a second. I think the broader question that partly was, in a way, could you also do this from observations alone without the big simulations? I guess that was partly behind.
Well, people have done that using so-called model replacement, or you could avoid having any parameterizations and try to learn the full parameterization suite from the observations. Yeah, that would be possible. I think that would prove to be an under-constrained problem. And also, observations here are with a grain of salt, since in detail, those observations depend a lot on the assimilating model. So, yeah.
Yeah, I would just add that, as a machine learning problem, this column locality assumption is really key, because it basically turns a short data set into millions and millions of samples, each column. And so what that means then is that you can use the physics, the sort of dynamics of the model to really expand the size of your training set. Whereas if you're doing sort of a time step or full model replacement, you're limited by the length and time. You only really have one whole globe per time step. And so your number of samples is much smaller. So I think that's one concrete thing that trying to work with a physically based model does for us.
Fantastic. I think this is a good time to wrap this up. Duncan, did you want to come in?
Yeah, I just thought it might be, for the kind of broader discussion around using these techniques for improving and speeding up climate models. We talked about drift and how that's going to be even more important, obviously, in climate simulations. Now, GCMs have had this for since they started, and you have physical parameters in there that you can tune, right? You get the top of atmosphere balance right by fiddling with the cloud cover scheme or so. And I guess you don't have those knobs if you have a neural network representing your cloud scheme. And I wondered if you had any thoughts about how you might go about that in the future, or if you just hope that will get learned by the neural network somehow.
Mm-hmm. Well, okay, so I'll take that as a question to me, since it seems like it's mostly relevant to my presentation. So I guess first I would say that the machine learning correction is sort of complementary to improving physical parameterizations. The better you make your physical parameterizations, the less the machine learning correction has to do, and therefore maybe the less it's likely to introduce any further drifts. And maybe then the role of the machine learning is to be able to correct sort of subtle regional biases that you might not even have seen without destroying the good things that the physical parameterizations are doing. But it's also the case, as I said, that we do know that there are ways to control the machine learning parameterization. So as I said, the neural net is sensitive to its seed. And so that does suggest, for instance, that we could use a sort of a genetic approach of selecting the best seed. If the problem with doing that is it can take a year or several years to really accurately constrain what the drifts of even a coarse resolution climate model are. And so it's dangerous to sort of select a seed based on performance for a month, and then the next month that seed wasn't necessarily the best choice. And so a lot of the question there is like how to do this without having to do many thousands of years of simulation. And so I think those are great problems, I think, for a broader community, and ones we'll be interested in. And I'm almost sure that someone else will be the first person to figure out the right way to do that.
Great, fantastic. I'd like to thank Chris and Noah again for two really interesting talks. It was a great session, and I'm glad we got everyone on despite technical difficulties. Before we dash off, I would just invite people to come back next week. We have great speakers next week as well. So Claire Montaglioni from University of Colorado Boulder and Gavin Schmidt, the director of NASA GIS, will talk. And they're both also the co-founders or in some of the founders of climate informatics who thought about some of these problems for a longer time than many of us. So it should be another great session. But thanks again, Chris. Thanks, Noah. And we hand back to Bastian.
Thank you.
Thank you, Philip. And a big thanks also to our speakers, Chris and Noah. We hope you enjoyed today's webinar, and we'll be launching a quick poll that you can use. And in the meantime, let me say that we have a few interesting webinars coming up. So at 7:30 today, we have a webinar in our AI for Health series. And then, as Philip mentioned, we have another webinar next Wednesday in AI and climate science. Please have a look. We've pasted the information in the chat, and we hope to see you there. Thank you for joining today.